Hello everyone, it's really great to be here. This is my first time at Black Hat, so it's an incredible honor that I can share my research here with you. My name is Pierre Hattenberg. I'm a vulnerability researcher in my spare time, mainly interested in hardware and firmware security, sandboxing and input validation, and you can find some of my work on my website. I'm a master's student in computer science at Eindhoven University of Technology. And the work that I'll be presenting today is part of my master's thesis. So in this talk, I'll be occasionally referring to Pci Express terminology, but in the interest of time, in case you're not familiar with it, just think of Pci Express as a packet switch network that connects your CPU to your peripherals. Now, Thunderbolt is an external PCIe-based interconnect, and it was developed by Intel and Apple in 2011. Now, being PCIe-based, it enables direct memory access I/O to the peripherals, and so it's the first external interconnect that allows use cases such as connecting an external GPU to a laptop, connecting 5K monitors, accessing high-speed external storage at its maximum performance. And well, the first two versions, they were mostly exclusive to Macs and used the mini display form factor. Thunderbolt 3 is the first version to be widely adopted among both PCs and Macs, and it uses the USB-C form factor instead, thereby allowing not only Thunderbolt devices, but also DisplayPort and USB-C. Now, DMA is a very powerful concept. It enables high bandwidth, low latency use cases by putting the burden on the peripheral for copying the requested data directly into system RAM. But at the same time, this could also pose a security risk. And this was actually the case with Thunderbolt 1. For Thunderbolt 1, all the attacker had to do was basically connect a peripheral and then get unrestricted read and write memory access. Now, as a result, the attacker could get access data from encrypted drives, and to gain persistent access, they could install a rootkit. DMA attacks are generally well understood. First started with FireWire back in 2004, and over the years gradually moved to Pci Express, including all its form factors, such as M2, Express Card, and eventually Thunderbolt. So the threat model that we'll be talking about tonight is brief physical access to a victim system, also known as an evil mate attack. And some of the real-world scenarios that you can think of are, for example, leaving a laptop unattended in a hotel room while you're out for dinner, or desktop systems sitting in an office, and at some point a cleaning crew comes in and has brief unfettered access. Now, in case you're wondering what such an evil cleaning crew might look like, I included a picture right here in the slide. So this brief physical access, the industry has implemented several protection measures over the years to protect against this so-called opportunistic physical access. So let's briefly go through them. First one is really simple. You put a password on your BIOS, and well, that should prevent the attacker from making unauthorized modifications when you get physical access. Then there's Secure Boot. Secure Boot focuses on cryptographically verifying all components in the entire boot chain, starting from the OS bootloader to the kernel, and finally the device drivers. There's Boot Guard, which focuses on cryptographically verifying the BIOS itself. And there's Full Disk Encryption, which enables you to encrypt all your data so that when an attacker gets physical access to your laptop, they can disassemble the SSD, but still cannot access the data without knowing the correct password. Now, to counter the DMA attacks that we've seen in the previous slide, Intel introduced what they call Thunderbolt security levels. And these security levels are intended to protect the entire thing that you see right here. So let's dive a little bit deeper in the Thunderbolt security architecture. Security levels, it's really an access control system. So if you connect a device to the laptop, then as a user you will see this pop-up right here. It will let you identify the device and then make a decision whether or not you would like to enable PCIe tunneling. Now, Thunderbolt security levels rely on Thunderbolt devices authenticating to the host, and these devices do this using the parameters shown right here. The most important one being the Universal Unique ID, or UUID. Now, this number is intended to uniquely identify any single Thunderbolt device. And also it's defined to be fused in silicon, so it shouldn't be easy to change. So Thunderbolt security levels is a multi-step system. As a user, you can select any of these in the BIOS. So let's quickly go through them. Well, SL0 basically is no security, so essentially the same situation like with Thunderbolt 1. There's SL1 user, where device authorization is based on the device UUID. And this is actually the default settings on all Thunderbolt equipped PCs. Then there's SL2. It's the same as SL1, but it adds challenge response mechanism. SL3 disables all Thunderbolt connectivity, but allows USB and DisplayPort devices. SL4 is intended for use with Thunderbolt docks. So when you connect a dock, you cannot daisy chain any additional Thunderbolt devices through that dock. And finally, if you're using SL1 or SL2, you will get pre-boot protection for free. So that means that any devices that you've previously authorized will also be usable during boot time, while the rest will be blocked from accessing your system. Now, security levels, the security level scheme is mostly known for protecting against device-to-host DMA attacks, but since it prevents malicious devices from accessing the PCIe bus, it actually prevents against other inherent attack factors, such as, well, peer-to-peer DMA attacks, PCIe spoofing to target vulnerable device drivers, and TLP source ID spoofing. So concept-wise, security levels is really a powerful and much-needed protection scheme. Right, so introducing Thunderspy. So previous research you can roughly divide into two categories. The first one, before security levels, they primarily focus on PCIe level DMA attacks. After the introduction of security levels, they mostly focus on tricking the user into accepting malicious devices. Now, Thunderspy is a new class of vulnerabilities that breaks Thunderbolt protocol security, and it's really the first attack on Thunderbolt security levels. So what we're presenting today is 7 vulnerabilities and 9 scenarios to actually practically exploit them. Right, so the first step in our research was to find out how Thunderbolt works. Now, Thunderbolt is a proprietary standard, so if you try to look up protocol specifications, you will not find them. And if you try to look up diagrams that will tell you how the what the hardware architecture is like, you will not find that either. So the first thing that we did was dissecting various Thunderbolt devices and Thunderbolt equipped systems. Now, eventually we came up with this diagram that I'm showing here for future research. So starting with the Thunderbolt host controller, the Thunderbolt host controller on the PC end connects to the PCH, and the DGPU and iGPU take care of generating a DisplayPort signal. Now, on the other hand, there's the USB PD controller, which is a third-party chip, and this controller multiplexes between Thunderbolt and a USB from the PCH as appropriate. Now, the device side is actually kind of a mirrored version of what we see on the PC. So the signal comes in and the Thunderbolt device controller then demultiplexes it to PCIe on the one end. And if the device has two ports, Thunderbolt again on the other end, so that you can connect another Thunderbolt device or a USB or DisplayPort device. Right, so let's have a look at some Thunderbolt devices. We have had a look at various Thunderbolt devices, starting with very simple eSATA to Thunderbolt dongles to storage solutions to eGPUs, and they were pretty much all the same. But this NetStore Thunderbolt NVMe enclosure really had a nice design. You could immediately identify all the chips, so that's why I'm taking it here as an example. Our prime suspect is in the top left corner, the Intel Thunderbolt controller, and we see a USB PD controller, Texas Instrument TPS, one for each Thunderbolt port. There's a SPI flash, which we'll be talking a lot about later, and I2C, which apparently has been routed by the NetStore people to easily accessible paths. So that was really nice. And there is a interface which appears to be JTAG, but well, to answer your question, no, it doesn't work, sorry. So the Intel Thunderbolt controller is, well, in this case, it's really a special model because it supports both running in host and endpoint mode. And, well, it's from the Alpine Ridge generation, so it supports DisplayPort 1.2, HDMI 2.0, USB pass-through, and USB power delivery. Now, in terms of analyzing the hardware architecture, this particular chip is not very attractive to have a look at least not initially, because it's a BGA package and there's no public data sheets. So yeah, we actually moved on to the other chips first. The TPS is actually quite the opposite. There's just a public data sheet that you can have a look at, and you can actually talk to this thing over I2C. So, for example, to get firmware identifiers, the current operational state, and I think there are even some registers in there that allow you to change the current output voltage. But I haven't really looked much into that. Now, the SPI flash is, of course, very interesting, and we'll be talking about it a lot more in the rest of this presentation. Of course, we dumped its content, and well, what we found was the Thunderbolt 3 controller firmware. And what you will immediately notice when you dump this firmware is a section called DROM, or device ROM. Now, this device ROM contains all the parameters that we've seen before, which are important for Thunderbolt device authentication. But the question is, of course, is the UUID also part of this? Now, the answer is yes, but only 2 out of 8 bytes. Still, we would like to know whether there's a signature and whether we can change any of this without breaking that signature. Now, to answer the first question, yes, there's a signature, there's a public key and signed digest. Changing the public key doesn't really work, so probably the fingerprint is embedded somewhere in silicon. But still, well, it would be interesting to find out what we can change without breaking the signature. So what is covered by the signature? Well, not the DROM, because when we do in-system programming, we can basically construct entire arbitrary identities for the device, and well, then you can create some nice identities like shown here in the screenshot. And this was quite puzzling at first because when you apply vendor updates, for example, updates that you download from a website, then the DRAM is actually part of the signature check, or when you do in-system programming, it is apparently not. Now, the second vulnerability is also quite interesting because, for example, the vendor ID you would expect to be tied to a certain vendor name, and the same applies to the device ID and the device name. Well, apparently that's not the case because you can make up completely arbitrary values for both entries. So, well, I had another look at the Intel white paper on Thunderbolt security, and there was this interesting section on the unique ID number. And it said every Thunderbolt 3 controller has a unique ID fused in silicon during production. Now, we already know this is not true because we can change 2 out of 8 bytes, but there was this interesting emphasis on Thunderbolt 3. So I had a look at Thunderbolt 2 devices, and well, to answer your question, yes, this is the UUID in plain text, and no, it's not covered by any signatures. So essentially what you can do is spoof both Thunderbolt 2 and Thunderbolt 3 devices. Well, once you spoof a Thunderbolt device that has been previously authorized by the user, then the system will accept your malicious device, and then you get full DMA access. So this is how we got to Thunderbolt Thunderspy vulnerability 3 and 4, and we've documented how to exploit these in these exploitation scenarios. So let's have a look at the device controller firmware. We see a jump address on top, which differs depending on the mode that the controller is running in. There's a secure key dictionary, which maps an 8-byte host UUID to a 32-byte key. The DRAM section, PHY configuration, the public key, the signed digest, and there's a section which comprises the TPS power delivery firmware. So that's really interesting because that means that the Thunderbolt controller and the TPS share the same SPI flash. Now finally, there's some scratchpad section, and this section is used to temporarily store firmware updates that you apply from the host. So let's have a look at some Thunderbolt equipped systems. We've had a look at all major vendors across 7 generations of systems, and we had a look at 5 generations of Thunderbolt controllers, starting from Thunderbolt 2 with Falcon Ridge, all the way to the latest Ice Lake Thunderbolt 3 controller. They were all pretty much the same, but the Lenovo ThinkPad V1 had a nice clean layout, so that's why I'm showing it here. Most of the components will be familiar to you, but there's of course the most important part in the top right, where we see the Thunderbolt controller, slightly different TPS version than we saw in the devices, and of course the SPI flash hosting the controller firmware. Now, for the host controller, the key questions are, as a user, you can select a security level from the BIOS. So that kind of seems to suggest that the BIOS stores the security level state. And for security level 1 and 2, well, these require storing device UUIDs. So that raises the question, where is the device ACL stored? So let's have a look. Well, the host controller firmware is pretty much the same as the device firmware, but there are a couple of important differences. For example, the first one is that the device, that there's a device ACL listing all of the UUIDs that are allowed, and there's no secure key dictionary, which is pretty interesting because in security level 2, these keys are stored on the OS disk, and it means that, or seems to suggest that with pre-boot and authentication, devices are still authorized based on the UUID only. Now, what was more interesting is another part we found. the host security level configuration. And yes, it's there in plain text, and no, it's not covered by any signatures. So all the attacker would have to do is patch the host controller firmware to, for example, disable Thunderbolt security or restore Thunderbolt connectivity when it was disabled by the user. Now, spy flaggers are really interesting devices, and they usually have multiple methods to support write protection. Now, this win bond we encountered in many Thunderbolt devices, and this particular one supports actually 4 write protection methods, including what is called one-time program. Now, one-time program allows it to turn the spy flash into a read-only memory. And this is really interesting because it says special order, but we found that these samples that we have still appear to ship this kind of support. So that's how we got to vulnerability 6, because, well, as an attacker, what you could do is exploit vulnerability 5 to override the vulnerable security to no security at all. And then you can simply turn the spy flash into a read-only memory, thereby preventing the user from ever changing, ever turning on Thunderbolt security again. So to summarize, the Thunderspy attack methods can be divided in 2 categories. So the first attack method requires only brief access to the laptop, only 5 minutes to reprogram the host controller firmware. It does not require any access to victim devices. Attack method 2 is kind of the inverse, so it does not require reprogramming the host controller firmware, but it only requires 5 minutes of physical access to one of the victim's vulnerable devices. So the impact for both is really much the same. So you get unrestricted read and write memory access. You can access data from encrypted drives. And to enable persistent access, you can exploit vulnerability 6, or you can install a rootkit to remove the dependency on Thunderspy altogether. Right, so here's a demo where we show attack method 1 in practice.
So what we have here is a Lenovo P1, which was purchased last year. And as you can see, it's in sleep mode. Yes, it's been locked, so I don't know the password. And the password isn't empty either, as you can see. So that's all good. What we're gonna do now is turn over the laptop so that we can reach the backplate. And we unscrew the backplate. Right, there we go. So now I'm going to attach my spy programmer, which is a device called BusPirate. And it allows me to interface with the spy flash that is storing the Thunderbolt controller firmware. So attaching the BusPirate to my attacker laptop. And now we're going to use a tool called FlashROM to get the firmware from the spy flash. Right, so now I have a dump, and I'm going to feed that dump to a tool that I wrote, which is called Thunderbolt Controller Firmware Patcher. And so as you can see, apparently the Thunderbolt controller was set to security level 1, which is the default security level on all Thunderbolt laptops. And I'm patching it now to an insecure state. And so as you can see, it says SL0, which means all Thunderbolt security is disabled. Now we're going to write back the firmware to the spy flash. Now this might take a bit because FlashROM will be trying various methods to program the spy flash. And as you can see, eventually it will succeed. Okay, so now we've written our custom firmware to the spy flash, and we're detaching the spy programmer and putting back the backplate onto the laptop. Turning over the laptop and opening it up. Now, as you can see, it's still up and running. You still cannot get into the laptop. And here I'm attaching my Thunderbolt-based attacker device. Now what you see here is a device that will be attacking the laptop. And we're going to use that device with a DMA attack tool called Pci Leech, developed by Frisk. And here I'm loading a kernel module into the memory of the laptop, which allows me to bypass Windows lock screen. We're entering no password, and there we go. We can get into the laptop.
All right, so let's recap the Thunderbolt security levels. On the left, we see the public definition. Now, let's talk about what we actually found it to mean. So SL1, device authorization based on the UUID. Well, this UUID, it's not really so unique because you can spoof them. And no, the UUID is not actually fused in silicon. Now, SL2 adds challenge response. Sure, that could work, but well, you can simply copy the keys from the device spy flash. There's SL3, disabling all Thunderbolt connectivity. Granted, that would work against cloning Thunderbolt devices, but when the attacker gets a hold of the laptop, all they would have to do is reprogram the host controller firmware to disable Thunderbolt security entirely. SL4 was a bit puzzling to us because really all you would have to do is, well, simply unplug an existing device or just pick another Thunderbolt port. And pre-boot protection, well, all security levels are broken, so yeah, this protection really has no effect. So, like you've seen in the demo, I used a tool that I wrote, Thunderbolt Controller Firmware Patcher. You can actually have a look yourself. It's up on my GitHub repo. And there's Spy Block, which allows you to toggle on-flash write protection. You can also get it from GitHub. So let's talk about affected systems. All Thunderbolt equipped systems shipped between 2011 and today are vulnerable. This definitely applies to all PCs released between 2011 and 2018. They are fully vulnerable. All Macs running Windows and Linux are as well. Now, some systems that provide Kernel Dma protection, they are partially vulnerable, and we'll be talking about them in a bit. macOS is partially vulnerable, so really you should verify whether your system is vulnerable using either spy check or by following the manual verification steps on our website. Right, so Intel's response to Thunderspy was Kernel Dma protection. So this was quite underwhelming, and I'll be showing a bit why that is. So Kernel Dma protection is an opt-in DMA remapping measure for Thunderbolt devices. And according to Intel, all you need is Windows 10 Etium 3 or later, or an up-to-date Linux kernel. So let's have a look how that works. Well, normally when a device does DMA to the host, it does that directly to the I/O addressable region. And when Kernel Dma protection is enabled, there's an IOU-MMU in between. So devices, malicious and legitimate alike, cannot read or write outside the boundaries which have been set by this IOMMU. So all in all, that sounds pretty good, but there are a couple of caveats. Kernel Dma Protection is a partial mitigation only. Specifically, it does not mitigate Thunderspy vulnerabilities 1, 2, 3. So this really exposes the system to a bad USB style of attacks. Now, most importantly, it not only requires an IOMMU, but also BIOS support. And we found that this BIOS support is only exclusively available on systems, not all systems, but some systems that ship since 2019. So basically what Intel is saying, well, you know, just buy a new laptop. Well, basically that means that about 8 years worth of systems remain vulnerable to Thunderspy forever. And this really didn't make sense to me because a lot of these systems feature an IOMMU, so technically they are capable of supporting DMA remapping. So what we're releasing today is Thunderspy 2, which is not an attack, but a proof of concept protection that brings Kernel Dma Protection to roughly 6 years worth of systems. So it includes all systems that have an IOMMU, including if they provide Thunderbolt 2. And the first implementation that we'll be releasing is an experimental UEFI extension. Just drop it in on your EFI system partition, and it will work with Windows 10 and recent Linux kernels. Now, the protection level that it provides is similar to officially supported systems. It does not protect against boot time attacks, but screen locking and sleep mode are again covered. If you're using Linux, we're working with the Linux kernel hardware security team to bring kernel level mitigations to Thunderspy. And meanwhile, Linux users can use the Thunderspy 2 UEFI extension. When you're using secure boot, you can sign it using your own keys, and you can combine it with measured boot, for example, heads, for additional security. Right, so we're now going to show a demo of Thunderspy 2 applied onto a unsupported machine.
This is a Dell XPS 15 purchased in 2018. Now, there have been no vendor updates that enable Kernel Dma Protection onto this model, so we've applied Thunderspy 2. Now, when we have a look in MS Info 32, it indeed says Kernel Dma Protection has been enabled. So we lock the screen, and now we're going to attach our Thunderbolt attacker device, and then we'll attempt to perform our DMA attack against the laptop. Now, Windows has detected what it calls a driver DMA violation, which means it caught us reading outside the memory range assigned by the IOMMU. So, Kernel Dma Protection is working as intended.
So, what's next for the future of Thunderbolt-based interconnects? Well, a number of issues remain unaddressed, starting with Thunderbolt vulnerabilities 1, 2, 3. There's really no means to distinguish between legitimate and forged DROMs. So devices could look physically okay to the user, but they could still be tampered with. And well, Kernel Dma Protection is implemented as a replacement to security levels by Intel. And a side effect of Kernel Dma Protection is that when you connect a device, this device will be immediately given PCIe tunneling without actually interacting with the user. So yes, it does protect against DMA attacks, but it does not protect against, for example, a malicious device spoofing PCIe IDs to attack vulnerable drivers. Does not protect against TLP source IDs spoofing. So yeah, these are important issues to have a look at, and they probably affect both USB and Thunderbolt 4. Now for Thunderbolt 4, we know that Intel will now require Kernel Dma Protection to mitigate Thunderspy. So the good news is if you buy a system with Thunderbolt 4, you are guaranteed to have Kernel Dma Protection. But still, backward compatibility likely means that both USB 4 and Thunderbolt 4 will still be affected by the issues that we mentioned here. Now, there are some ways to potentially mitigate these remaining issues. Well, starting with the Thunderspy vulnerabilities, essentially everything is in there in the firmware to fix this issue. There's a public key and a digest. So all that Intel would need to do is share the scope of the digest, and then the driver or UEFI could verify firmware authenticity before enabling PCIe access. Now, regarding Kernel Dma Protection, well, in the interest of practical use, I would say it's okay to allow all DMA devices on boot, but during OS runtime, I would initially suggest to null route all new DMA devices, so you actually don't assign any I/O range just yet. And then you require screen unlocking and explicit user authorization. And only at that point, you can have the IOMMU assign an IO memory range. Now, to counter vulnerabilities in drivers, you could use virtualization-based security. I think Microsoft is currently working on that with Kernel Dna Protection, and I could see the Linux kernel doing this in the future as well. And finally, to counter TLP source ID spoofing, I would suggest that the Thunderbolt controller implements a second mechanism such as PCIe ACS. So just simply enumerating all downstream devices and then verifying that the TLP source ID matches any of those devices. Now finally, for USB 4, of course it would be a good idea to implement a UEFI toggle that controls Thunderbolt signaling. But, well, I don't know if anyone from Intel is watching, but when you do, please maintain the state in the BIOS only. So the takeaway that I would like to give you is that, well, Thunderspy is a new class of vulnerabilities breaking Thunderbolt security. There's no fix from Intel, so really check if your system is vulnerable using SpyCheck or verify using the steps listed on our website. There's the full vulnerability report as well, in case you're interested. Thunderspy 2 is not an attack, but an experimental protection, which shows that laptops that have an IOMMU but no Kernel Dma protection are technically capable of supporting this protection. And the first implementation that we're releasing today is a UEFI extension. Now, whether we like it or not, the future is apparently PCI Express. So that really allows some nice use cases, but for USB 4 and Thunderbolt 4, well, adequate protection schemes remain absent for now. So I hope that when these technologies end up in consumer products, the issues that we've mentioned here will be addressed. Right, so that's it for today. If you have any questions, you can reach me on Twitter or just ask me here in the Q&A. Thank you for joining. Hi all, thank you for watching. Before moving to the Q&A, I'd like to make an announcement, a little update to Thunderspy 2. As part of Thunderspy 2, we're presenting 2 options today that aim to bring Kernel Dma protection to Thunderbolt-equipped systems that do not ship Kernel Dma protection, but do satisfy all hardware and firmware requirements. This should, well, basically bring Kernel Dma protection to roughly 6 years worth of systems.
if you're interested in helping out in testing our experimental patch, it's available on our website right now, thunderspy.io. And well, we would very much appreciate your feedback. So moving on to the questions. So I'm reading the question: if the system doesn't have an IOMMU, is there any mitigation short of entirely disabling Thunderbolt? Well, no, I would say no. Basically, there are fundamental issues with Thunderbolt device authentication. And, well, that basically defeats the only protection scheme that Intel provides on all systems released before 2019. So the security levels that we discussed in the presentation. And Thunderspy breaks these security levels with the root cause being Thunderbolt device authentication not working. So unfortunately, no. If the system doesn't have an IOMMU, there is nothing we can do except maybe waiting for Intel to change their minds and, well, maybe bringing a software workaround for this. Okay, I'm hearing that we're going to need to wrap it up. So if you have any more questions, please ask them in the chat or just, well, you can reach me on Twitter as well. Thank you.